Yeah. Before I started, did you guys get my email that we're doing online today? An email last night.
I'm just hoping that we drills us on the students.
Jordan, you got my email yesterday?
Yes, I'm pretty sure I did. Let me check. Yeah. Monday meeting online. Yeah, I got that. 7:22 last night.
Students coming in. You still owe me the attendance, okay? You can keep this online, okay? Morning, Tyler. Morning. Jack. Morning, Jack. Maria. Morning. Out, not too bad. All right, well, let's wait for 2 minutes. And I have made exam, and it's not too scary, okay? And I'll upload last year's exam after our lecture today, okay? Sorry, I forgot to do it yesterday. Student made what type of problem they did last night, and I think we finalized with that. Homework today, and part of it, deflection, which we talked about, and also column design, which we'll get into. We'll finish that on Wednesday, and Thursday we'll do a review and going through the exam today. Okay, so that's the tentative schedule. Right. And about the finals, and I noticed that several students you can do it before the final day, which is the 17th. That's okay. And we might have to ask you guys to schedule testing to do the exam, and they will proctor you. And I will send the place before you start it. Okay. So that's that. Well, the time is 9 a.m. So let's get started. Morning, everyone. Thank you for being patient and joining this lecture online just this week. I'm traveling and right now on campus, and I'll be hosting a conference this week. So unfortunately, I have to do this online thing. But I think we are okay in terms of content. We have only the column left. Okay. And I was whispering before you guys all join us. And this is about our exam schedule. Okay. Let me say this again. I fixed the final exam last night. By the look of it, it's a 4.5 problem. When I say 4.5, really I decided to make the second one, the fill in the blank. So I look at the fill in the blank problem. You might have to do some calculations, right? So I think that's counted as a 4.5. And if you join in late, the lecture is being recorded anyway, okay? So you can watch it on my YouTube channel, which I'll send you the link right after lectures. All right, 2 more uploads. Now I'll post last year's final exam right after our lectures, hopefully by noon today, okay? And then I'll also post the homework, which will be our last homework. The homework will have 2 components, but one will be on the deflection calculation, which we talked about, last week, or the week before last week, actually. And we'll get into more of a column design, which will finish this Wednesday, okay? Now, on Thursday this week, we'll do a review session, right? We'll go over the exam I posted today, and we'll answer some questions. And then next week, we won't have any lectures, okay? You guys can study, but if you have any urgent needs, you can email me or text me, okay? I can set a one-on-one meeting with you guys, all right? For those of you who want to take the test earlier, let me say this again, please, right now it is a time to schedule a test center so they can proctor you. I will email them the exam papers ahead of time so they will be ready, okay? All right, apart from that, any questions for me, folks? Anything for me before I start? Anything? All right, quiet. Okay, oh good. All right, so let me get right into it. Column design, okay? So let me here see this iPad thing and share. Here we go. And that's it. Okay, so we have talked about the column design. All right, we have talked about, oh, sorry, I don't know what's happening here. Let me try this again. So in terms of column design, we have mainly talked about the different stress state, okay? So when I say different stress state, what I really mean by is that in terms of a interaction diagram, I don't know how I can jump outside this Zoom thing. Let me see if I can get a, this new Zoom thing is not really good. Give me 1 second, folks. Okay. All right, you all have to excuse me for 1 moment, okay? Let me see if I can fix this business here. Okay, stop sharing. Do this. Okay, every time give me this trouble. All right, let's switch different screen here. No, that should work. All right, so share screen again. Try this. But then, what's going on? Okay, this is good. All right, okay, so now we have this screen now, and let's talk about why this jump outside thing is just, hold on a second, folks, sorry about that. This new system here is messing me up. Why can I cannot do this thing. Stop sharing. Okay. All right, I might have to just do this though. Really bad. Too smart. Why this is going on? Come on, you. Nothing. Okay. All right. I gotta do this cable thing again. Okay. Let's see if I can do this cable thing. All right. Let me see. Do you guys see anything screen-wise? Do you see the notepad I'm working on?
No, I
No,
don't.
right? Okay, let me see if I change something here. All right, okay. Do you see it now? Do you see it?
Yes, I do.
All right, good deal. Okay, so finally it's working. Apologize, okay? It's new tech thing. Every time I switch different network, gave me this trouble. Anyhow, let's continue, okay? So last time we talked about the force moment interaction diagram, right? Just a quick recap what we have learned last time, right? So we have learned that if I have a force versus moment diagram, right? Supposedly I should have a linear failure line, right? And that is because if I look at the cross section here now, and I have a force acting on this cross section, these are bars, okay? Dashed line are the bars, force acting on the cross section, right? So I'm trying to make sure that my stress exerted, right? So sigma, which is equal to P over A. Now here is plus a moment that PE, P is the force, E is the eccentricity, CL here, and this is distance here, and multiply by the distance to the tensile fiber and divided by I, and that is the moment caused the stress, right? So all we are trying to do is to make sure this stress will hit the concrete compressive strength that is F prime C. Remember? And when we have this equation, we say, you know what, this is kind of like an equilibrium. So we can balance it out by removing this portion and divide everything both sides by F prime C. And once you divide F prime C by both sides, what you really have is P over A F prime C and plus something here, PE Y divided by moment inertia I and F prime C. Right hand side, you're only left with 1, right? Only left with 1. And we also say that if you switch, right, switch P to an Y and switch PE and to be, well, PEY in this case, well, no Y anymore. Let's just say this is H because that's the tensile fiber anyway, right? So switch this to be X, right? Eventually you will have is Y over A F prime C plus X over I F prime C multiplied by 2 over H. And that is our equation, right? So if this is the case, and we call this Y critical or P critical, right? And we call this M critical or X critical, whatever you call it, then eventually you have these two numbers here. So this is so-called, well, let me be more explicit. So if I call this P critical and this is M critical, so this is M critical here, and this is P critical here. And once I have that, the straight line is this linear line here is my failure envelope. And we also talked about it, right? If I have a data point right here inside this failure envelope, that means I have a safe column, right? My capacity is, or applied moment and interaction is below my capacity, right? So I'm safe. So this is safe. And outside this region here, and this is not safe, right? So this is failure, failed, right? So fails, okay? And this way we will know if our design is good or not, right? Or the other way, if we know a section and we know the capacity, we can check if the applied loading exceeds the requirement or not, right? So that's really it. But the problem we have, or in the sense of in the reality we have, is that this moment diagram is not that ideal. This moment diagram, right? This P and M interaction diagram is not that ideal. Okay, in what sense is not ideal? In this sense is that first, this equation right here, right? So if I draw out here, say this equation right here is only, this is based on, only based on a linear materials response for the concrete, okay, for concrete, okay? What does it mean? It means that if I look at the stress strain curve, right, for concrete, it should go this way. Okay, all this, that the linear line you're seeing here, all this are based on the linear relationship. But in reality, the concrete, right? So actual materials response, oh, sorry, of concrete, it goes differently, right? Is in a linear response. So sigma in terms of stress and epsilon here, it goes linear first and reach to a peak and gradually drop over, right? So here I have my critical strain epsilon Cu. At peak here, I have my strength F prime C. So considering this, the real interaction diagram P and M doesn't look like at all the original, right? Original curve. Instead, right, if I use a blue curve to show that the real failure envelope of a reinforced concrete column, okay? Reinforced concrete column. Start from a point here, and let's call this point A. Okay, and this is called pure axial load. Okay, so we call it pure axial load. Okay, what I mean by that means there's no eccentricity. Eccentricity equals to 0. All right, and then you gradually increase the moment, right, by increasing the eccentricity, right? So you're basically shifting the eccentricity. Okay, and then you see another point right here, somewhere in a halfway here, and I call this the point of zero tension. And I'll explain, okay? Point of zero tension. Okay, point of zero tension. All right, and then afterwards, you keep go this way and keep increasing the eccentricity, okay? To a point, and this is the belly button right here, okay? Belly button right here, that's the peak, okay? I call this point C, and this point is so-called a balanced failure. Okay, balanced failure. And I also explain, okay? And then after that, you keep increasing, right? And then at this is the peak, right? So it has to go back now, and you reach to a different point again on this diagram. This is called D, point D here. And this point D here is called tension control limit. Sounds familiar, right? And don't worry, I will explain, okay? Tension control limit. And once you pass that tension control limit, you keep going, finally, you reach to a point of E, okay? Point of E, okay? So this point E is called what? Small compressive zone, or small compressive zone, or E, eccentricity equal to infinity, approaches infinity, right? So we call it small compressive zone. Okay, small compressive zone. So all these are some stress state in the concrete, in the reinforced concrete column. Okay, now I said to explain, right? So let's take a look at these points, right? So in the first point, right? First point, we have this A here, and that's called pure axial load, right? Eccentricity equal to 0. So what's really happening is at point A, and if I use my strain, right, as an increment or slash eccentricity E here, Kyle, I might have to ask you to mute yourself, okay? So it won't create static noise, okay? Thank you. And then if this is the strain increment strain, we depart from A, right? And that is the pure axial load, right? Pure axial load. It just means that if I look at the stress distribution, all right? If I look at the stress distribution, okay? Well, let's just say actually, how about strain distribution, right? So let's use strain diagram, right? Strain diagram. Okay, what it looks like. So for A, since it's pure compression, okay, let me keep this curve. So pure compression, so I have a pure compressive strain along the entire section, all right? So that's called state A, all right? As I move forward, right? So let me just do another comparison or a company drawing. So if this is the section here, and this is center line here, so I want you to see this, okay? And then the force right here is acting, say, this is right here, right in the middle, along the center line, okay? So this is A. So if I say this, let me zoom out a little bit so you see both. So this is, let's call it eccentricity, okay? Eccentricity, or location of axial force, okay? Location of axial force. Different definition, but same thing, right? So A, it looks like this, right? Pure compression, no bending stress at all. No bending stress at all. Now, if I keep increasing, so let me go here. All right, and again, this is center line. And I start increase my eccentricity, right? Shift my loading towards right, for example. It can be in the left as well, okay? It doesn't matter symmetric. I'm just putting in one direction, okay? Keep shifting towards right, create an eccentricity E, and then my strain diagram changes, all right? How it changes, right? So you recall a bending means what? What does bending mean? It means that the plane section remains plane, right? Straight line remains straight. So it just means that my line was originally here, and now I shifted, rotate a little bit, right? By the angle, right? By angle, right? And now my entire cross section still sustaining a compressive strain. At extreme point, bottom right here, there's just zero strain, right? So zero tension, meaning it was at the junction of tension. There's no tension at all, barely entering the tension region. Okay, so that is B, point B. Okay, point B. All right, so let me just put it on top, and so now interfere with my beautiful drawing here. And then next step, right? So this is from A to B, and then from B to C. Do I have enough space? CD. Okay, I think I will just a bit tight here. Okay, so now I keep shifting my concentrated force, right? Keep increasing my eccentricity E here. Okay, now what happens is that I have more bending stress, right? So I look at the strain diagram, you know, it was here and now it will lean towards more of the other way, right? So I start to see what? I start to see strain in tension now. Okay, I start to see strain in tension. This is compression still, but I start to see strain in tension now. All right, and it gets to a point at C where the peak is at, right? So I started seeing tension after B, right? So this is basically tension region, right? In this region, I start to see tension, right? And now just at C, what happened is that my strain in steel, epsilon S here, reaches to a yield strain of 0.00207. Okay, 0.0207. Just so you know, this is what we talk about. This is grade 60, okay? If it were different grade, the strain is different, okay? So as soon as the steel reaches yield strain, my bending moment will reach the maximum point, okay, on this failure envelope, all right? And since it is at a strain equal to 0.00207, we call this balanced failure, okay? Balanced failure. So you say, Bob, what do you mean by balanced failure? It means that at this point, right, my steel is at the borderline between elastic and plastic. So it's balanced, right? A little bit tip over will become plastic, a little bit under will return it to its elastic state. Okay, so that is the strain diagram for C. Now you guessed it, right? So we just keep playing the game and keep increasing the distance, right? So now the axial force is further apart, okay? I think I exhausted almost my real estate, but anyway, let me just say, and it goes a little bit further. And when that happened, and we call this D, is that, okay, the strain, the steel keep increasing, and now it becomes a different number, okay? Become a different number. And this number, my friend, you are very familiar with. Okay, this number, my friend, you're very familiar with. And this number here, epsilon S equal to 0.005, 0.005, okay? And that's why it is called the tension controlled, okay? Tension controlled limit. Tension controlled limit, right? So you know the 0.005 business, right? Tension control limit, okay? Now, we keep increasing. And now you realize that in my diagram, I already exhausted all my real estate, meaning my axial force is gonna actually come out of the section. You say, Bob, how is that possible? Well, yeah, sure, it is possible in the sense that I still have some covering on the column, but the force, right, the nominal force, for example, if I have a concentrated force on the beam, right, something like this, and then although the beam is still sitting on top of the center line, but my reaction force is falling outside this column, right? That could happen, okay? And we call this E approaching to infinity, right? And in that case, you think of it, right? So we progress from point A to B to C to D, and you realize it is just the tensile strain, right? The tensile side of the strain keep increasing. And when they reach the stage of E, eccentricity equal to infinity, what really happens is that I have a very, very small compressive zone, okay? Almost zero, but I have very, very small compressive zone. Now, most of my stresses, well, always in the wrong side, always my stresses are in tensile. Okay, and we don't have a number for this, but we do know this C here is almost zero. Okay, it's not exactly zero, it's approximately zero. Okay, all right, so now you have it. There you have it. That is our diagram, interaction diagram. Okay, interaction diagram. All right, so this is what we're looking for. Essentially, given the section, okay, given the section, and this is really for analysis, okay? We are only asking you guys to know to do analysis of a column, right? So this is analysis of column. Analysis of RC column. Okay, that is to give a section. Given the section, you should be able to draw this moment diagram, and also calculate the numbers, right? Calculate the P and M numbers at these points A, B, C, D, and E. We need to get numbers out of it, right? As we always say, define, quantify, conclude. We have the definition now. We need to quantify, right? We need to come up with mathematical description of it. Okay, before we go there, right? I want you to pay attention one more thing. Now you look at this diagram here, right? Let me zoom in. You look at this beautiful diagram here, right? Just like a belly button, right? Nice and curvy and something like that, right? So what really happening is now based on the strain level, right? I can ask you guys to give me the stress reduction factor now. Remember, stress reduction factor now. Okay, so how about, well, look at it, right? So if I am between A and C, if I'm in this range, okay, well, might as well just connect the straight line from 0 to C, right? So I call it O, okay, to C here, right? So within this range, my strain, you gotta remember, right? This epsilon S equal to 0.00207 yield strain, right? And for grade 60, right? So here, it means that I'm in the compressive zone phi equal to 0.65. Remember? Compression controlled. Right? Compression controlled. Okay. Now, if I connect another line from O to D, and D here is what? Tension control limit, remember? And here, folks, epsilon S equal to 0.005, right? So if we were in this region, we call it phi equal to that equation, remember? Phi equal to that equation, remember? And this is called transition zone. Say, Bob, what equation? The interpolation equation we'll talk about later, okay? This is in the transition zone, just like in the beam analysis, remember? Bending analysis, right? But after the strain exceeds the tension control limit right here, right? We say tension control and phi equal to 0.9, okay? 0.9. All right. Yeah, so that's it. That's the axial force moment interaction diagram for a column. And phi, which is stress reduction factor. So you calculate P, you calculate M, you multiply them in front, or you multiply phi in front of all of them, right? And you get a nominal capacity for your column. And that is the name of the game. That is the name of the game. Okay. So up to this point, we're talking about theories, and this is the concept, right? Like we said, define, quantify, and conclude, right? We need to quantify them. So how to calculate them? How to calculate them? This is how, okay? So after we know the concept, right? I'm taking a look again at this interaction diagram, right? So let's take a look at this interaction diagram. Okay, and precisely, let me show the side view of the section, right? So if this is my column, right, very slender column, remember, slender column that we have to care about both axial force and bending moment. So assume that, let's just go a little bit extreme. Assume that the axial force is right here, center line of the column right here, and I have eccentricity of E right here. So needless to say, I have created a moment, right? I have created a moment already, and this moment equal to P multiplied by distance E. And I have a negative side of it, meaning in tension, and positive side of it in compression. Remember, that's our definition, right? So if I look at the top view of the section, so if this is side view, okay, and the top view of section looks just like this, nice, beautiful rectangular section. And now if I call this B, dimension-wise, I call this B, okay? And be careful, right? Whenever I call it B, you realize that B is in the width direction. And why is that? Because this direction here is called H. That is along the same direction that P moves. That is along the same direction that P moves. All right. All right. Okay. So now before we do anything, we realize that in column, there's always going to be almost symmetric reinforcement, right? Because you don't know, right, which way it's going to go. It can lean towards right, and the force can lean towards left. So in the typical column section, reinforced concrete column, you see a symmetric reinforcement arrangement. So usually it looks like this. 4 bars, right? Each at the corner, 4 bars. And then the center line looks something like this here. Okay, and we have the definition of the concrete cover D prime. D prime. Okay, and then we have the definition of depths again for D. Say, Bob, how you define this way? Look, where's my axial forces at? My axial force is somewhere here, right? So from the top view, you don't see it, right? You see a circle. It's supposed to be along the center line here, right? And then this is positive force going downwards. And from the top view, you should see the end of the arrowhead, right? Cross, like end of the arrowhead. So P is going downward like that, right? In and out of plane, right? So this is go in the plane, okay? Go in the plane. So that tells you that my compressions ought to be somewhere here on this side, right? My compression somewhere in this side, and left side is tension. Left side is tension. All right, now, so the bars here are the compression bars, so I call it D prime, right? These are the tension bars, so I call it D. Okay, and the depth is defined between the distance of the bars to the compressive side of the section, right? So as we defined before. Okay, that's how I made the definition of that. So look at the strain diagram, right? Look at the strain diagram. So with that, I say mapped out the strain, and I do this, and instead of beam, I have a column now. So I flipped everything, right? I flipped everything, right? So I have now the concrete strain somewhere here in compression, right? At failure, this is epsilon Cu. Okay, at failure, it is epsilon Cu. All right, and now tensile stress somewhere here, and let's call it epsilon S for the steel. Okay, epsilon S for the steel. And my actual compressive zone is C right here. So tensile strain right here and compressive strain right here. Okay, so that is my strain diagram. So for stress, right? So this is strain. For stress, right? What we did before for beam are the Whitney stress block, right? Whitney stress block. We're going to do the same thing, right? Same thing. So here I have my Whitney stress block here, and it's rectangular stress distribution and in compression, right? My sign is a little bit messed up, but you know, it's in compression, right? A equal to beta 1 C, just like in column, right? There's a beta 1 coefficient, okay? And it has a full-blown strength of 0.85 F prime C developed in a compressive zone. All right, and then I have now compressive reinforcement right here, okay? Compressive reinforcement right here. So I have Fs prime, okay? Stress in the compressive reinforcement. Now tensile stress, I have the tensile stress from the steel, okay? So this is my stress diagram. This is my stress diagram. All right, so looking at my stress diagram, I say, what about internal forces? Just trying to find a total for each component, right? Total for each component. So I keep dragging it down. I want to see the internal forces, All right, so from the compression of the concrete, I know that it located right here in the half A, right? I have CC, compression force, and this is distance half A away from the compressive fiber. And then I have a compressive stress from the bar, so CS, go this way. Okay, all right, and this distance right here is D prime. Okay, now I don't know if half A is bigger than D prime or not. I just draw it out there, right? It can be the other way, but it doesn't really matter, right? That's the definition of it. And I also have a total tension force from the steel in tension side and on the, at the tension side, and this distance right here, fellows, is D. Okay, is D. All right, I may have messed up the strain diagram in terms of this need to line up. Okay, this is a bad line up, but you know what it is. This is strain. Okay, this is level strain. So I zoomed, I enlarged it a little bit. Okay, so these are distance D here. Okay. All right, so now that is my internal forces. So internal forces. Okay. All right, so you say, Bob, why are you bothering drawing me so many diagrams? What are you trying to get at? I'm trying to get at is I look at these diagrams, right? Especially the final forces diagram. And note that this is called internal forces. Okay, this is called internal forces. Now, in terms of equilibrium, right? Equilibrium. So equilibrium, right? What is equilibrium? Means that free body diagram, internal has to be equal to external. All right. So in terms of axial direction, what do I mean by internal has to be equal to internal has to equal to external, right? So what is internal? Internal, I have a concrete compression force CC, right? Plus the steel in compression and minus the steel in tension, right? So these are the sum up of my internal forces. Now, what is external? The external force is applied compressive force P here. All right, compressive force P here. And just to differentiate, this is Pn because this is a nominal capacity. It hasn't taken the phi, strength reduction factor yet. Okay, this is nominal capacity. Okay, now that's for axial direction. For bending direction, right? So for bending, okay, for bending direction, right? Or I wouldn't say direction anymore. Let's just say axial forces, axial and bending, right? So internal, what kind of bending moment I have? Well, let's take a look, right? I have my compression force cause the bending moment. So force is CC, right? And I want to sum moment with respect to tensile reinforcement, right? But that's a little bit too much. So I am going to sum moment to my neutral axis right here, or to my center line right here. So this is half H. Okay. So let me just say sum moment with respect to center line. Okay, it is matter of fact neutral axis, but I just want to be a little bit explicit. Okay, easier for you, right? So if I sum the moment with respect to the center line, axial force CC will cause a moment of half H minus distance half A, right? That's the location of CC here, right? And then plus, because this right here is what? It's this direction, right? It is what? Clockwise direction, right? And plus a CS, compression force from the steel, multiply half H minus ds prime, okay? D prime or ds prime, all right? So again, that is what? Clockwise, both are clockwise, right? And now look, I also have the tensile force TS generated moment, okay? And the distance is, of course, half H. Sorry, D minus half H, right? D S minus half H. This distance right here is D minus half H. Okay, ds minus half H. Now, be careful. If I'm looking at the moment, right, the force is going up. So the moment is in this direction. And again, it is clockwise. So plus sign, plus sign, plus sign. So that is the internal moment. On the other hand, the external moment should equal to Mn, right? Moment apply, and that is essentially Pn multiply the eccentricity E here. Okay, all right. So these two sets of equations, right, tells us, right? So sum, okay, that tells us Pn, which is the nominal axial force capacity, equal to a 0 point, or I mean CC plus CS minus TS, right? And CC, which is the total compression force, equal to 0.85 F prime C AB. Remember? Long time ago, right? In a galaxy far away in the beam design, this is what it is, right? Then plus AS prime, the compressive reinforcement, right? Multiplied by the FC prime, sorry, FS prime, that is the stress in the compressive reinforcement, subtract 0.85 F prime C. Okay, and you're asking why, Bob? Why I have to minus that? Well, go back to doubly reinforced section, right? Remember, when you take the bar out, you have to fill the concrete back in, okay? So you fill the concrete back in here, so you have to subtract it out. We will take care of the stress in the compressive reinforcement, okay? And minus the tensile forces, that is AS, reinforcement, the tension side, multiply Fs, stress in the tensile reinforcement. Okay. All right. So that is for the axial force. Now, bending moment, Mn, again, equal to Pm multiplied by eccentricity of E, and that should equal to Cc, which is 0.85 F prime C AB, multiplied by distance, half h minus half a, and plus as prime fs prime minus 0.85 f prime c multiplied by distance of half h minus ds prime, and plus a tensile force ts multiplied by distance ds minus half h. And my friend, when I say d, I truly mean ds, okay? I just was lazy a little bit. Okay, s represents steel, okay? Not much, just steel. All right. Okay, so in the sense, we already given you how to calculate the P and M on this diagram, Okay. All right, so you were given the equation to calculate these points A, B, C, D, right? P and M on this point A, B, C, D, E. Okay. And at this point, you start to freak out again, right? And very typical, right? So say, Bob, you give us the equation, right? What number should I plug them in, right? How can I calculate? I mean, your entire envelope is dependent or determined by the strain in the reinforcement, right? By the strain of reinforcement. Now, how should I know which number I put in here, right? Which number I put in here, all in these complex equations, right? So let's take a look at the example. All right, let's take a look at the example. Okay, so last but not the least, example. So example, all right, given the column section, and we're going to do analysis for column, okay? Not really a design. So everything is given the column section, okay? Given the column section below. Okay, and we need to determine several things. Okay, and before I say determine, I show you the section, right? The column looks like this, a very nice rectangular section, right? And I have a height of h, okay, right here, 20 inches. Okay, and now if I say this is the height, be careful, right? On top here, this diagram, h is this direction, right? So now for this problem, h is this direction. So my axial force is here. Okay, axial force here, top. All right, and now I have my width of the section. What did I have in terms of my width of the section? Let me see if I note it down somewhere. 12 inches. Right, so this is my width of the section of 12 inches. Okay, B equal to 12 inches. Okay, I have a stirrups that looped around bars, and I have 4 number 9 bars in terms of a column reinforcement. Okay, this is in and outer plane, right? So 4 number 9 bars, and I have stirrups loop around it. Okay, and you see that when I draw stirrups, there's a hook, okay, going this way, and another hook going this way, and hook it to close it here, okay, to close it here. And technically, we call this a tied column. Why is that? Because the stirrups acting just like a tie and tie the bars around, the bars around. All right, and now before we start, okay, let's define some things, right? So the center line is right here in this direction, and we call this x-axis, okay, where the axial force locating along this line here, and we just call this y-axis, okay? And knowing that h is 20 inches is larger than the 12-inch width, we also call the x of strong axis. Why is that? Because along or perpendicular to the strong axis, I have the highest height, right? I have the height, okay? And naturally, the y-axis, you should have learned it from steel design, and this is called weak axis, okay? And before I start everything, when I put my force P along this line here, everything I talked about here in this case is with respect to the x-axis or strong axis. Okay, that's the premises. Okay, all right, so that is a strong axis. Okay, very, very important. Okay, in the exam, you have to be clear. You have to read the problem clearly, okay, to see which is my axis. If I were to put the P here, then I will ask you to do the y-axis. Okay, but I am not. I'm putting the P along my y-axis direction, so that is talking about everything axial force and bending moment with respect to the x-axis. X-axis. Okay. All right. So we have the drawing, have the section. We haven't even talked about what we're asking, right? So let's take a look. So before I have my concrete 4 KSI concrete bar, 60 KSI grade, 60 bars. And first thing first, I need you to determine PN, MN, okay? And that is corresponding to the balanced failure. And you say, what is balanced failure? Well, point C, right? Point C. Okay. And 2, PN, MN, okay, at, well, we'll say that somewhere along tension failure region. Oh, Bob, you got me confused again. What do you mean by tension failure region? Well, you look at the diagram, remember? This is P, this is M, right? And I have my curve here, a belly button right here. This is point A, B is here, C is a peak, D is somewhere between here, peak, and the closure point E here, right? The tension failure region is where? Tension failure region is, I cut it into 2 zones, right? This is the tensile zone, which is actually from C to E. And this blue shaded area is my compressive zone, okay? Compressive zone. So A to C. Okay, so that is the differentiation. Okay, differentiation. Okay, so all we are asking is just find some points between C and E. Some point between C and E. Okay, now if I want to be a little bit picky, right? I say, to be precise, I want you to find a point, right? A point. Find a point. I shouldn't capital A, right? A point that has epsilon s greater than 0.005 means what? Means what? I'm forcing you to find a point that between D and E, between D and E. Okay, so that's problem number 2. Number three, it was asking you, so find out a PN, MN for a point in the compressive region. Okay, and that is to find some point between A and C. And last but not least, problem number 4 is to find PN, MN for a pure axial load. And you should know immediately when I say pure axial load, I mean A, point A. Okay. All right, so these are the questions, right? So I look at the question, I say, you just so much complications, so many words. Bob, all you're asking is to find this diagram, isn't it? Just asking us to draw the diagram out, right? You're just asking us to find point A, B, and C, and D, and E, and then quit yank my chains, right? You just wanted me to do everything. Well, you got that right. I want you to show the points and finish this curve essentially, okay? That's what we're asking you guys to do. And in exam, all right, in exam, this is all you need to do is to find A, B, C, D, E and draw the curve, right? Draw the curve. You say, Bob, how do I draw the curve? Well, you think of it, right? Once you have A, B, C, D, E, I'm drawing this nonlinear curve nicely, but if you have trouble, right, your hand shakes and whatever, right, you can do this, right? You can just connect them straight line, right? Can you do that? A, B like that, B and C like that, this, you can do that, right? Both ways are fine. but you need to give me numerical values for A, B, and C, and D coordinates, right? Where exactly they are at, where exactly they're at, okay? All right, so let's find them, shall we? Let's find them, right? So first thing first, solution, solve, right? Now talk about point 1, right? So I want to find point C first, because this balanced fader is easy, right? So balanced fader point. It's the easiest point to find. Okay, and how do I find that, right? So first of all, I have my strain diagram, right? And strain diagram dictates that my concrete has reached the failure CU equal to 0.003. And this is the bottom side of the concrete. I don't know what it is, but my strain in the bars epsilon s here equal to what? 0.00207. And this is for grade 60, okay? Grade 60, 207. All right. Now, what is my depth? What is my depth? Well, I don't know, Bob. You have never talked to me about it, right? You just give me a height of h is 20 inches. And how am I supposed to find my depth? Well, it's not that hard, you see, because I only have one row of number 9 bars to be precise, right? You look at the section. I have one row here and 2 number 9 bars, isn't it? 2 number 9 bars. So we talk about for one row, the concrete cover is what? The concrete cover is 20 minus what? 2.5 inches for one row of bars. All right, and that is 17.5 inch of a depth. Okay, there you go. All right, so given the depth, that is 17.5 inch right here. So save me the trouble right here. And what I'm going to do to use that strain diagram to see what is my compressive zone C right here, right? So compressive zone C here should equal to the similar triangle business, right? Epsilon Cu divided by epsilon Cu plus epsilon S and multiplied by the depth of D, and C equal to epsilon Cu 0.003. Bottom here 0.003 plus a 0.00207 and multiply the whole depth thing, and the depth is 17.5 inch. So I got my C equal to 10.3 inch. All right, and then my actual compressive zone is beta1 C, right? And beta1 for 4,000 psi concrete, that is 0.85 multiplied by 10.3 inch. So I have this one here, 8.76 inch. Okay, 8.76 inch. Not too bad, right? Not too bad. Okay, now with that, I look at the stress in the steel. I know that stress in steel has reached the yield stress, which is Fs equal to Fy, and that is 60 KSI. 60 KSI, right? So now this is 60 KSI in terms of stress. What about my compressive strain, right? Don't forget, I still have my compressive reinforcement to figure it out, right? To figure out. So Fs prime compressive stress equal to Young's modulus of steel ES multiply epsilon S prime. Yep, you guessed it. You have to dust out the doubly reinforced section problem, right? Understand what's happening here, right? So ES here, and the strain in the compressive bar, use that similar triangle here, right? So epsilon S equal to C minus ds prime minus C and multiply, divided by C and multiply epsilon Cu. Okay. All right, now bring the number in. Fs prime equal to ES. What is the Young's modulus for steel? 29,000 KSI, right? And multiply, bracket inside 10.3 inch in the C. And D prime, I told you in the problem, should be 2.5 inch. If I haven't, well, take a look. It's got to be one row of number 9, right? Again, so this is 2.5. Okay, so this is 2.5. One row, right? If it's 2 row, 3.5, right? 3.5. Anyway, 2.5 minus 10.3 inch, okay, and multiply 0.003. Now, you do the calculator business, hit the buttons, Fs prime equal to 65.9 KSI of a strength in the compressive bars. Now, when you look at this number, you say what? You say, oh boy, I'm in trouble. Why is that? Because this number ladies and gentlemen, is greater than the yield strength of the bar, which is 60 KSI. Okay. Okay. And should you panic? No, you should not. All right. Why is that? Because in column design, ACI says, right? So I'm just going to put out here, ACI says, and you don't have to find the specific clause in ACI code. Just know that ACI says when fs prime greater than fy, capped it. Remember in double reinforced section, we said the same thing, capped it, right? Fs prime capped at yield strength of 60 KSI. Okay. It is allowed to have S prime bigger than the yield strength. And for column design, it is allowed to have that, but you capped it. You allow your strength to be Fs prime equal to 60 KSI, 60 KSI, okay? This is very important. Set a limit and you're done. Set a limit and you're done. All right, so this is what we have, right? This is what we have. Now, given Fs prime, I have find out most of my stress state, isn't it? Concrete right here, CC, right? C, compressive zone, A, compressive zone known, Fs tensile stress, Fs prime compressive stress. So I start doing my equations, right? So knowing that now CC equal to 0.85 F prime C A B, and I know I'm doing too much time. I'll finish this, I'll be done. Okay, 0.85 multiplied by 4, 0.876 inches, 12 inches, and that gives me 357 kips. All right, so that is the compression force from concrete. Okay, all right, folks, I'm running out of time, so I'm just gonna close right now, okay? But we'll talk about this on Wednesday, continue to talk about this on Wednesday. The course lecture today is recorded. I send you a link right afterwards, and you take a look and ask me questions on Wednesday, okay? Thank you all, and see you on Wednesday. Stay behind if you have questions, okay? Stay behind if you have any questions.
Just Bob, I have a question.
Yep.